This lecture talks about basis and dimension of a matrix. So let's talk about a set of vectors, right? A set of vectors that spans a vector space V. And then if you cannot remove a vector from a set of vectors that is a spanning set for a vector space V, then you have a minimal spanning set. And those vectors are linearly independent. Because you have a set of vectors and those vectors spanning V, vector space V. And then if you want to move one vector from a set and you cannot do that, then you have a minimal spanning set and those vectors are linearly independent. Well, what is a basis of a matrix or a basis of a vector space? So the vector, by the definitions, the set of vectors v1, v2 to vn is a basis for a vector space if and only if the set of vectors here are linearly independent. Also, this set of vectors spans V. Okay, there's two conditions for a set of vectors to be a basis of a vector space. First, the set of vectors are linearly independent. Second, the set of vectors spans V. Now let's consider this set of vectors in R3. The question is, do the sets of vectors form a basis for R3? Well, let's find if this set's independent. If this set is a spanning set. So to answer these two questions, I want to put these vectors here in a matrix. And I will augment this matrix with a generic vector v1, v2, v3. And then I'm going to reduce this matrix to answer this question. Are these vectors linearly independent? Are these vectors spanning set of R3? Okay. So I reduce this to 0, 1, 0, 0. B1 is the first pivot row, and then this is good. So this is the second pivot row, should be 0, 1, 0, 2, B2. And then R3 should be R3 minus R2. 0, 0, 1, 0, 0, 1, 1, 1, B3 minus B2. Okay. Now the third row is a pivot row already. By the definitions, that means we can stop here for now to evaluate this system. So we know that this is a free variable. That means the system is, and we don't have any zero row with non-zero entry on the right side. That means the system is consistent. Okay. If the system is consistent, means the set of vectors is a spanning set. Of R3. So it is a spanning set of R3. We checked one of the conditions, right? How about the second conditions? Are these vectors linearly independent? And to answer these questions, we need to see if they're going to be linearly independent. If you set all of this, if B1, B2, and B3 are 0, you will have a unique solutions, right? Do you have a unique solutions? No. You have non-trivial solutions. If you have non-trivial solution, that means this matrix here I said this is matrix A. So matrix A is singular. If matrix A is singular, that means the sets of vectors here are column vectors are linearly dependent. So we know, and then this answer our questions no, right? And this is a yes. So this set of vectors spans R3, but they are not linearly independent. That means I can conclude that this set of vectors do not form a basis for R3. Okay. In order to form a basis for R3, they have to be linearly independent. Also, they have the spanning set of R3. And from using the system AX equals to B, I evaluate this system, and I know that this system will have non-trivial solutions. That means this matrix A here is not singular, is singular, and if it's singular, then the column vectors are linearly dependent. That means these vectors here are not forming a basis. Well, then the next concept is about the dimension of a vector space. So if V is a vector space and V has a basis consisting of n vectors, we say that V has dimension n. The dimension of V is n. A subspace 0 of a vector space has the dimensions of 0. And V is said to be finite dimensional if there's a finite set of vectors that spans V. Otherwise, we say that V is infinite dimensional. Okay, so you have a set of vectors that form a basis of V, then the number of vectors in that set is the dimension of V. If you have a subspace 0, you know, a vector space always have 0 as a subspace, then the dimension of the 0 subspace is 0. If the number of vectors in a basis for the vector space is finite, then we have a finite dimensional, then V is finite dimensional. If you have an infinite number of vectors in a basis for V, then V is infinite dimensional. So this is the definitions of what is a basis of a vector space and how can you determine the dimensions of a vector space. Okay, so if you look at R2, let's look at an example of R2. In R2, you need to have 2 vectors to form a basis in R2. So the dimensions of R2 is 2. Okay, and then if you look at R3, then you need to have at least 3 vectors in R3 in order to span R3. So then the dimensions of R3 is 3. So in general, the dimensions of Rn is n. What does it mean? That means you need to have at least n vectors forms a basis for Rn. Okay. All right, let's look at some of the theorems that connecting a set of vectors with the dimensions and bases. First theorem, if you have a set of vectors v1 to vn is a spanning set for vector space V, then any collections of m vectors in Vn where m is bigger than n is linearly dependent. So again, if vector space V only needs n vectors to span the whole entire vector space, then any set of m vectors where m is bigger than n, you have more than vectors that you need in order to span a vector space, and those sets of vectors will be linearly dependent. So reasonably, you can move one or more vectors from the set So then the remaining set still spans the vector space. And if V is a vector space of dimension n, positive, then any set of n linear independent vectors span V, and any n vectors that span V are linearly independent. Again, if vector space has a dimensions n and n is greater than 0, then if you have a set of n linearly independent vectors, that set will span V. Also, if you have n vectors that span V, then that set of vectors have to be linearly independent. This is the relation between the dimensions of a vector space with the spanning set and with the linear independence. Well, the next theorem is if V is a vector space, has dimension n, again positive, then to say no set of fewer than n vectors can span V. For example, if you're in R3, you need to have at least 3 vectors to span 3. Okay, at least 3 vectors that can span R3. Any subset of fewer than n linearly independent vectors can be extended to form a basis for V. So in R3, if you only have 2 vectors, then you can always come up with 1 more vector. So then the set of the 3 vectors will span V. And then any spanning set containing more than n vectors can be pared down to form a basis for V. So that means if you have 4 vectors here in R3, you can always pare it down to 3 vectors that is form a basis for V. So I can erase one of the vectors, so the remaining 3 vectors will form a basis for R3. Okay. Well, let's look at this example here. So given 3 vectors in R3, and you want to show that these 3 vectors here are linearly dependent. How can you show that? You show that the 3 vectors are linearly dependent when you can put them into a system, right? 3, -1, 4, 2, 6, 4. And just for linear independency, I just need to put them into the system, AX equal to 0, homogeneous system. Okay, and I just reduce it. So I move it up here, and then move it down, and then 3, 4, 4. Okay, and then I do some row operations in order to determine whether this system has only trivial solutions or it has non-trivial solutions. I don't have to solve for it. I just need to know those information. So the next is R2 minus 2 R1, and R3 minus 3 R1. Okay. So we have 1, -1, and still 6. Here, still 0, 0, 0. Here, I have 0. 3 minus 2 is 5. Right? 2 minus 12 is 10, -10. Here I have 3 minus 3 is 0, 4. Minus 3 is -3 is 7. 4 minus 3, 18, which is -14. Okay. And then my next step is I want to reduce the third row even a little bit more. So R3 will be the same as R3 minus 7/5 R2, right? Because 7 minus 7/5 times 5 is 0. So I have 1, -1, 6, 0, 5, -10. And I have 0, I have 0. And then 7/5, I should have 0 here. So at this point, I know that I have one free variable. If I have one free variable, that means the system has ax equal to 0 has non-trivial solutions. If it has non-trivial solutions, means A is singular. If A is singular, it means all the column vectors are linearly dependent. First, so they're linearly dependent, I just show that, right? That means x1 and x2 and x3, one of the vectors depending on the other two, or two vectors depending on one vector. Well, the next thing is, I want to show that x1 and x2 are linearly independent. Okay, how can I show that? I can show that by putting them into a matrix. 2, 1, 3, and then 3, -1, 4. Okay, again, I augment it with this. And then as you see that using this work that I have done here. So by definition, like doing some similar row operation, I would have this two matrix here. Right. So I would have 1, 0, 0. I have -1, 5, 7. And I augment it with 0. Similar row operation, I would have this. So I just cut these two columns here and augment it with 0 because it's always 0 there. Okay, at this point, again, I can always do another row operations, right? Say 0, 0, 5, and 0. And then I do the last row operation. I should get this. This is R3 minus 7/5 R2. Okay. All right, so at this point, I have, this is the 0 row, is fine, and I have, this is pivot position, right? And I don't have any free variables. So there's no free variables, that means the system here, no free variable. If no free variables, that means this matrix here is non-singular. That means the two column vectors. The system, I call the system Bx equals to, this is B, right? X equals to 0. Bx equals to 0 has only trivial solutions. That means B is singular. Oh no, I cannot talk about singular or non-singular. That means x1 and x2, right, are linearly independent. So I can talk about the singular or non-singularity here because B is not a square matrix. So, but I know that if this system has trivial solutions, that means all the column vectors are linearly independent. So I know that x1 and x2 are independent, but the set of x1, x2, and x3 are linearly dependent. Okay. So then you want to ask, what is the dimensions of the span of x1, x2, and x3? So because x1, x2, and x3 are linearly dependent, and x1 and x2 are independent, then the span of x1, x2, and x3 is the same as the span of x1 and x2, because x3 is depending on x1 and x2. So then the span of this set is the span of this set. And since x1 and x2 here are linearly independent, then the dimension of this span, there's the dimensions of span x1, x2, x3, right, equals to 2. Because you need at least 2 vectors, x1 and x2, to span this span of x1, x2, and x3. So then the next one is give geometric descriptions of the span of x1, x2, and x3. So you have x1 and x2 and x3, and they are in R3, right? Let's say this is x1, this is x2, okay, and x3 is the linear is a linear combinations of x1 and x2. So when you add or you subtract x1 and x2 with some multiples constants, you got x3. So x1 and x2 will form a plane. There's a plane that contains x1 and x2. And x3 is just another vector that is on the same plane. x3. Okay. So the geometric description of the span of x1 and x2 and x3 is span is a plane in R3 that contains x1 and x2, x1, x2, and x3. Okay. Well, in this case, because x1 and x2 are linearly independent, that means you can just need to use the 2 vectors x1 and x2 to create this plane. And x3 is a linear combinations of x1 and x2, because x1 and x2 are linearly independent. So a plane in R3 has dimensions of 2, right? Because you only need 2 vectors to span this span. Even though this is a set of 3 vectors, but because these 3 vectors here are linearly dependent, and you found that x1 and x2 are independent, that means x3 is the vector that depends on x2 and x3. If x3 is depending on x2 and x1, then x3 is a linear combinations of x2 and x1. If x3 is a linear combination of x2 and x1, then the span of x1, x2, x3 each is the same as the span of x1 and x2, right? And then the span of the 2 independent vectors in R3 is a plane. And since x3 is a linear combination of x1 and x2, I know that x3 is just a vector on the same plane. So this is an example on how you look at a set of vectors in a vector space, and how you evaluate whether a set of vectors linearly independent or dependent. How can you evaluate whether a set of vectors, can form a basis, right? of V of a vector space. How can you determine the dimensions of a space? You determine the dimension of a space using the least number of vectors that span the entire space. Okay. Well, in this case here, you only need x1 and x2 to span the space of x1, x2, and x3. Okay. So x1 and x2, so the dimensions is 2 because this is the minimum number of vectors that you need to span this space here. And again, remember the span of a set of vector is a subspace of R3. It's a subspace of R3, and in fact, it is a plane that contains the vectors x1 and x2. Okay. And then if you find out that a set of vectors is linearly dependent, then you can figure out which vector is depending on the other vectors. In this case, x3 is depending on x1 and x2, and you can see that x1 and x2 are the directions of the space. If x3 is depending on x1 and x2, that means x3 is a linear combination of x1 and x2. Furthermore, you can figure that the relation between x3 is a1 x1 plus a2 x2. Okay. So you can figure a1 and a2 so that x1 and x2, so that x3 is a linear combination of x1 and x2. All right, so this lecture talks about the basis of a vector space and the dimension of a vector space. The basis is a set of vectors that are linearly independent and span the vector space. And the dimension of a vector space is the minimum number of vector space of the vectors that form a basis. Actually, it's just the dimension, it's just the number of vectors that form a basis of a vector space. And we know that in Rn, the dimensions of Rn is n. That means you need to have at least n number of vectors to form a basis for any Rn on the vector space Rn.